Okay, this is Physics 16.2, the wave nature of light. When we think of waves, we think of wavelength, we think of frequency. We're also going to look at something called Doppler shift and the fact that light diffracts around objects. All these things have to do with waves. So we're also going to be looking at the idea of colors and color of light and color pigments and polarization. So wavelength. We're going to be looking at some new words like diffraction. You've probably heard of primary colors and secondary colors. We're going to also look at primary and secondary pigments, polarization, and we're going to learn a new law. So let's take a look at a short video here.
In 1665, Italian scientist Francesco Maria Grimaldi observed that the edges of shadows are not perfectly sharp. He introduced a narrow beam of light into a dark room and held a rod in front of the light such that it cast a shadow on a white surface. The shadow cast by the rod on the white surface was wider than the shadow should have been if light traveled in a straight line past the edges of the rod. Grimaldi also noted that the shadow was bordered by colored bands. Grimaldi recognized this phenomenon as diffraction, which is bending of light around a barrier. In 1678, Dutch scientist Christian Huygens argued in favor of a wave model to explain diffraction. According to Huygens, all the points of a wave front of light can be thought of as new sources of smaller waves. These wavelets expand in every direction and are in step with one another. A flat or plane wavefront of light consists of an infinite number of point sources in a line. As this wavefront passes by an edge, the edge cuts the wavefront such that each circular wavelet generated by each Huygens point will propagate as a circular wave in the region where the original wavefront was cut, as shown here. This is diffraction.
Okay, so color. So how does light and color relate? Isaac Newton noticed that when he passed a beam of sunlight through a glass prism, then we would get a spectrum of light. He reasoned that if it's the corpuscles of light interacting with some kind of unevenness in the glass that produce the spectrum, he figured that he should be able to spread it out even further by pushing it through a second spectrum, a second prism. Instead, what he found was that as the light passed through the second prism, it reversed, and the spreading of the light actually recombined to form white light. So he concluded that the white light, first of all, is composed of colors, and secondly, it's some other property of glass that causes it to separate out into colors other than the unevenness of the glass. So here we have a light spectrum ranging from red at about 700 nanometers up to violet at about 400 nanometers. The white light crosses the boundary from the air into the glass and then back into the air. In the figure, it's waves. Nature causes it to bend differently because if the wavelength is different, and each one is bent slightly differently by the glass, then it's going to come out at a different angle. It's the uneven bending that causes the light to spread out into a spectrum. So that's one of the supporting evidence that we can look at a wavelength of light and it's going to act in a predictable way. When we talk about combinations of light, if we look at white light is really a combination of other colors of light. So for instance, if we can adjust red, green, and blue light evenly and put it on a screen, the overlapping portion is white. So this color additive process is actually how we get color TV. We have little dots of red, green, and blue, and depending on what color they want, whether they want yellow, they'll do red and green together. If otherwise, they can get other colors, and if they want white, they'll just put all three on the screen. We call red, green, and blue primary colors. So the primary colors can be mixed to form additional colors, secondary colors, yellow, cyan, and magenta, and then a variety of colors beyond that. Again, these are secondary colors. So the yellow light can be made from red and green, for instance. And if we put yellow with blue, we get white. So yellow and blue are complementary. Whenever we have two colors that will make white light, we call those complementary. So in addition to yellow and blue, we could look at magenta and green, or red and cyan are all complementary colors. They add up to white. One of the ways we use this is in laundry. We could add something called a bluing agent. It's actually a little bit blue. So if your laundry's starting to get a little bit yellow, you add some blue, and the blue and the yellow are complementary to get the clothes back to being white. Now, apart from reflecting light and transmitting light, objects can also absorb light. So not only does the color of an object depend on the wavelength present in the light that illuminates it, but it also, in the object's colors, depends on the wavelengths that are absorbed by the light and what wavelengths are reflected. The natural existence or artificial placement of dyes in a material of an object or pigments on the surface give it its color. For instance, we have dyes that are molecules that can absorb certain wavelengths of light and transmit others. When light is absorbed, its energy is taken in and turned into other forms of energy. A red shirt is red because it absorbs all the other colors except for red and reflects the red. So let's talk a little bit about pigments and dyes. Pigments are different from dyes in the fact that they are made from minerals instead of plants. And pigment particles are actually big enough that you could see them under a microscope. So a pigment that absorbs only one primary color and reflects two from white light is called a primary pigment. A pigment that absorbs two primary colors and reflects one color is called a secondary pigment. So, primary pigments are the secondary colors. In the same way, secondary pigments are the primary colors. If we go back to our color wheel, we can see this. When the primary pigments of yellow and cyan are mixed, the yellow absorbs blue light and the cyan absorbs the red light. Now, if all the pigments are if all the colors of the lights are being absorbed, you don't get white, you get black. So it's kind of the reverse here. So the yellow pigment is mixed with the secondary blue. It absorbs the green and the red. And if all of the colors are being absorbed, you end up with black. So therefore we say that yellow and blue are complementary pigments because they would result in black. Cyan and red, complementary pigments because they would also result in black. You'll notice when we do a color printer, we don't use the primary colors that we would think of. We use primary pigments. We use yellow, magenta, and cyan are the colors that we use on a printer. For what it's worth, the pigments are usually suspensions, not solutions. And again, we could look at why certain things look the colors they do. Grass is green because chlorophyll reflects the green and absorbs the other energies, light wavelengths. When we look at the sky, it looks a little bit blue, again because the particles can spread the blue light more, and so that's reflected around and bounced around. We see that. The other colors come straight from the sun to our eyes, so as long as we're not looking right into the sun, we don't see those other colors. So green light and red light are not scattered in the sky. That's why the sun tends to look a little bit blue, yellow or orange. It's because those colors are coming through. Okay, so let's look at polarization of light. You may have noticed that light reflected off the road when you're looking through polarized glasses. If you were to rotate those glasses, you'll notice that the road first appears dark, and then it's light, and then it's dark as you turn the glasses around. You normally don't do that, you just put the glasses on, but if you were to rotate them, you would see this. It doesn't happen with the light from a lamp. It just cuts down the light, but the light is coming in all directions. Now, why does this happen? Well, one of the reasons is because the light coming off the road is reflected, and the other reason is that the reflected light is becoming somewhat polarized. If you think of polarized light, it means that we've eliminated the waves coming in a variety of directions, and now the light is basically only propagating out in one particular direction. And so you could kind of see through the diagram there, if it's in line with the lines that you're looking for, then all that light comes through. If it's across the line, then it gets cut down. So when you're looking at polarized light, you're basically eliminating a bunch of the lines. So it's cutting down on some of the light coming through. So the light's coming through. As long as it's trying to get through the slot in the direction that we want it to come through, all the light gets through. However, if we turn our line, basically this is what's polarizing, it basically will cut down on the ability of the light to get through. So when we have polarized lenses, what it means is that we only have the lines in one way. So not all the light gets through, only the light that is oriented to the grade of the polarized lenses. So the perpendicular, if they come in perpendicular to the slot, they're going to get blocked. Polarizing medium contains long molecules of in which electrons can oscillate or move back and forth. So light passes the molecules, the electrons can absorb some of the light waves that oscillate in the same way as the electrons. So this process allows light waves vibrating in one direction to pass through, while waves vibrating in another direction are absorbed. The direction of the polarizing medium perpendicular to the long molecules is called the polarizing axis. Only waves oscillating parallel to the axis can pass through. Ordinary light actually contains waves vibrating in all directions, and so perpendicular to its direction of travel. And so the polarizing medium basically cuts down on most of the waves and only allows the waves that are oriented in the same direction as the polarizing axis to pass through. So we're going to cut down about half of the light's amplitude, reducing the intensity of the light. Polarizing mediums produce light that is polarized, means that it has a single plane of oscillation. The medium can be said to be a polarizer of light, is called a polarizing filter. And when you look through the filter, one of the things you can do with this is if you have two filters, you could rotate them in relationship to each other and you could cut down on the light even more. So the reflected light contains a great deal of light. Okay, so anyways, that's why the road looks the way it does. Again, if we put a second filter through, we can cut down on it even more, which leads us to Malthus' law. Basically, Malthus' law says that if we put a second filter in, we could look at the intensity of the original light, I1 down here. If we multiply that by cosine squared of the angle, then we'll get another, and we're going to cut the intensity of the light down by another factor, which brings us to I2. So the intensity of the light coming out of the second polarizing filter can't be greater than the original intensity. It has to be less, and it's to be less by the cosine squared of the angle. So you can determine the orientation of the polarizing axis if you want to using the Malthus law. Okay, so last we look at the relationship between the wavelength and the frequency and the speed. Remember, speed is equal to wavelength times frequency. If you remember that, we're in good shape. They've already rewritten it to say that the wavelength is equal to the speed divided by the frequency. And the speed of light in a vacuum is going to be used c, 3 times 10 to the 8th. The frequency can be counted with extreme precision with lasers and clocks and so on, and so we're actually able to come up with a better speed of light. Now, all wavelengths travel the same, electromagnetic waves travel the same speed in the vacuum. And we can measure the speed of light anyways.
What happens if a source of light is traveling toward you, or you are moving toward the light source? You learned in Chapter 15 that the frequency of a sound heard by the listener changes if either the source or the listener of the sound is moving. The same is true for light. However, when you consider the velocities of a source of sound and the observer, you are really considering each one's velocity relative to the medium through which the sound travels. Because light waves are not vibrations of the particles of a mechanical medium, unlike sound waves, the Doppler effect of light can involve only the velocities of the source and the observer relative to each other. The magnitude of the difference between the velocities of the source and observer is called the relative speed. Remember that the only factors in the Doppler effect are the velocity components along the axis between the source and observer as shown above. To study the Doppler effect for light, the problem can be simplified by considering axial relative speeds that are much less than the speed of light. This simplification is used in the equation for the observed light frequency, f observed, which is the frequency of light as seen by an observer. This equation can be used only for situations in which the axial relative speed is much less than the speed of light.
Okay, so if we want to study the Doppler effect, problem can be simplified by considering the axial relative speed. Remember, the axis is the line that connects the two objects. The relative speed is whether they're getting closer or further apart. And we come up with our formula, and again, it only applies when the light is relatively slow. And so our formula then is going to be frequency times 1 plus or minus the velocity of the axial velocity, in other words, how fast they're closing or spreading apart over the speed of light. Remember, if that number v over c is 0, then basically the observed frequency is the frequency. So if the velocity, the actual velocity up there is 0, then you don't have any shift in the frequency. So we end up with what we call the Doppler effect. We could also rearrange it a little bit to figure out the Doppler shift, or the change in the wavelength is going to be equal to plus or minus v over c times the original wavelength. And we'll be using that equation in class. Generally, if things move away from us, we get a redshift. And if things are moving towards us, we get a blue shift. Out in space, we notice that most everything is redshifted, which means that we think that the universe is spreading apart. If the wavelength was blue shifted, then again we would think that things are are approaching us. Edwin Hubble was the one that came up with the expanding universe theory based on redshift. You notice that the spectral lines, not just one wavelength, but the whole wavelength of a particular star seemed to be longer than expected, and he assumed that that was redshift. And again, it doesn't matter what direction he was looking in, everything seemed to be redshifted.